We'll start with a very basic history of organic chemistry and see how best we can wrap up the lesson and look at types of organic compounds. So if you are joining us, you are welcome. We are just starting with this lesson. So if possible, get your pen and paper so that you can make reasonable notes as you follow along with this lesson. So let's say a little background history about organic chemistry. It was around the 18th century. So around the 18th and the 19th century. You will not believe what people actually had in mind during those times. There were examples of organic compounds like urea. And scientists had this strange belief that these organic compounds could only be produced by living creatures. For example, you should be a goat, you should be a plant to be able to produce an organic compound. So if you are not a goat, if you are not a plant, then you cannot produce an organic compound. That is what scientists actually believed in. So organic compounds like carbohydrates, lipids, proteins, urea can only be produced by what? Living things. Living things like plants and animals. Only these things will produce what? Organic compound. That has been the belief held by scientists all over these years. And they called that theory that they had the vital force theory. The vital force theory. So basically, the vital force theory promotes the idea that if you are not a living thing, you cannot make an organic compound. So it has always been that. So according to this theory, you couldn't make something like sugar or urea in the lab unless you are a goat or a tree. Yeah. So if you would want to make an organic compound, you should have a goat or a tree on standby. Only then will you be able to produce organic compounds like sugar and urea. So that has been a quite strange belief that they had at the time. But the good news came in 1828. What was that good news? In 1828, there was this German chemist called Friedrich Wöhler. He's a German chemist. His name is Friedrich Wöhler. That vital force theory that existed for a very long time, Friedrich Wöhler completely disproved the vital force theory. And how did he do that? He disproved the vital force theory by preparing urea in the laboratory. Remember, urea is an organic compound. But Friedrich Wöhler disproved the vital force theory by producing urea in the laboratory. And what did he use? He used inorganic substances to produce urea. So that has been the belief. So urea was produced by him. And he didn't do it with any fancy stuff. He didn't use plants, he didn't use animals. All he used was just some test tubes and a hot plate to produce this urea. So just that single experiment by Friedrich Wöhler completely destroyed the vital force theory. So the vital force theory was completely destroyed by Friedrich Wöhler by means of that single experiment that he did. So this event sparked the birth of organic chemistry as an actual science. How interesting. So had it not been Friedrich Wöhler's experiment, there wouldn't be organic chemistry as we know it today. So a big thanks to Friedrich Wöhler. And since then, chemists have been able to cook so many things from plastics to all other carbon-containing compounds like medicines that we use today. Because of that single experiment, scientists got to believe that, okay, so that means there are other compounds that could be made like painkillers, plastics, and other medicines that we know today that they believe they would be able to do. So that's quite interesting. So we thank Friedrich Wöhler so much. Good. So if you meet Fedushola one-on-one, what would you tell him? So that means had it not been his wonderful work, we wouldn't have this wonderful field of organic chemistry. So now that we've established the history or background story a little bit about organic chemistry, let's define organic chemistry. Let's define organic chemistry. What is organic chemistry? What is organic chemistry? Any idea about organic chemistry is? It is simple. So here's the definition of organic chemistry. Organic chemistry is the branch of chemistry that deals with the study of structure, properties, reactions, and preparations of carbon-containing compounds, especially those with hydrogen, oxygen, nitrogen, and sulfur and halogens. So when we say organic chemistry, it basically means the branch of chemistry that deals with the study of compounds that contain carbon. So if there is a compound that contains carbon, and you are studying those compounds and other related properties of those compounds, then you are studying organic chemistry. There are some few exceptions, those like the cyanides of carbon. Those do not fall under organic chemistry. So that's an interesting definition of organic chemistry. And the good news is carbon has some unique properties. Carbon has some unique properties. You see, we said organic chemistry deals with studying of compounds that contain carbon. But the question is, why is carbon the ideal element such that we have a dedicated aspect of chemistry for it? The reason is simple. Carbon has some unique properties. Carbon is able to form 4 bonds. Carbon is able to form what? 4 bonds. And it doesn't end there. It's also able to create chains, rings, branches, and also able to form double and triple bonds. So this is what we mean. Carbon is able to form 4 bonds. So if you know the electronic configuration of carbon, that is, carbon has an atomic number of 6. So 2, 4. So carbon being the central atom is able to form a bond with 4 other elements. So this is one unique property of carbon, form 4 bonds. Another unique property of carbon is this. It's able to form chains of carbon. So you can see that we have carbon atom here, another carbon atom, the 3rd carbon atom, then the 4th carbon atom. So this is a chain of carbon atoms. So carbon atoms linked with each other to form a chain. This is quite unique. Yes, very, very unique and special about carbon. Which other elements can do that? Then carbon doesn't end it there. It forms 4 bonds, it forms chains, and it's also able to form rings, like cyclobutane. So you can see that carbon is bonded to this carbon. So 1, 2, 3, 4. They loop over each other to form a chain, to form a ring. So that's another unique property of carbon. And carbon is also able to form compounds that are branched. So you have branches. You can see we have 1, 2, 3, 4 carbons. And then there is an extension from this carbon. So there is a branch over here. So that's another unique property of carbon. So carbon is able to form all of these stuffs. So we have carbon forming 4 bonds, chains, rings, and branches. So it's because of this unique property of carbon. That is why carbon has a dedicated field called organic chemistry. And carbon is also to form double bonds. Carbon can form what? Double bonds. And it doesn't end it there. It's also able to form triple bonds. Wow, that's very unique of carbon. So just look at these unique properties of carbon. There is no other element that is able to do this. There is absolutely no other element that is able to have all of these unique properties in one. So look at this carbon, single bonds only. Look at this carbon. There are triple bonds here. Then this has double bonds. So quite amazing. Then that doesn't end it here. So why is organic chemistry important? Why is organic chemistry important? Why is organic chemistry important? Sometimes when I remember my days in school, most of my classmates or even some of us, we used to ask, why are we even learning these stuff? Is it even necessary for us to learn about some of the things that we learned in school? But when it comes to organic chemistry, there are a lot of reasons why we can say organic chemistry is so important. Because think about life without organic chemistry. Life without organic chemistry. Can you imagine life without organic chemistry? I'll tell you why life without organic chemistry is a nightmare. If we live this life without organic chemistry, it's a complete nightmare, and I'll tell you why. The reason is this. Reason number one, without organic chemistry or organic compounds, there will be no food. Without organic chemistry or organic compounds, there will be no food. So bye-bye to foods, yes. So there will be bye-bye to carbohydrates and a big bye-bye to proteins and fats. So if there is no organic chemistry or study of organic chemistry, or there are no organic compounds in this world, there will be no food, because our carbohydrates and fats, our proteins, all of these contain organic compounds. So we need to understand these compounds very well to understand the food we are taking in. So that's one reason why organic chemistry is important. So at this point, if you are with us on the live stream and you have not subscribed to the channel yet, do your best to hit that subscribe button. Subscribe. Let's continue. Subscribe to the channel. Let's look at the second reason organic chemistry is important. The next reason is without organic chemistry or organic compounds, there will be no medicine. There will be what? No medicine. So without organic chemistry, there will be no paracetamol. There will be no painkillers, because all of these contain what? Organic compounds. So that's how beautiful or important organic compounds are to us. So organic chemistry, without it, there will be no medicine. And without organic chemistry or organic compounds, there will be no clothes, because cotton, polyester, nylon, all of these contain organic compounds. So you see how important it is: food, medicine, clothing, how important organic chemistry. Unless otherwise, you are someone from the prehistoric era. So you are so interested in prehistoric fashion. Even with the prehistoric people who are so interested in prehistoric fashion, I'm sure there are some elements of organic compounds in what they use. So organic chemistry is so important. So we can't do without learning organic compounds or organic chemistry. And then without organic chemistry, there will be no plastics. There will be no fuels. There will be no phones, no soap, no perfume, no chocolate. Chocolat. Yes. Without organic chemistry, there will be no chocolate. And I think chocolate is one of the favorite things of ladies. Yes, they enjoy chocolate a lot. So if you are a lady with us and you do love chocolate, but you don't like organic chemistry, then I think you should stop liking chocolates, because you should know that there are elements of organic compounds in chocolate, and in all of these things: plastic, fuels, foam, soap, perfume, chocolates. So organic chemistry is so important. We can't live without it. So we need soap, fuels, foams, plastics, fuel, foam, soap. Then we have perfumes. All of these contain what? Organic compounds. And then imagine this girl asking the guy, "Sweetheart, I want to eat chocolates." Yes, sweetheart, I want to eat chocolate. But she doesn't know that the chocolate she wants to eat contain organic compounds. Interesting times, right? Yes, so there are a lot of things we use around that we don't even know that contain what? Organic chemistry. Good. If you are with us, subscribe to the channel. Subscribe to Learner's Aid. And it doesn't just end on the things that we use like medicines and plastics. it extends all the way to our DNA and blood. Deoxyribonucleic acids. So our DNA and blood also contain organic compounds. So the organic, we ourselves, as you are sitting there watching this stream, you are made of organic compounds. Your DNA is what? Organic in nature. Your blood is organic in nature. So there is no way you can tell me that you do not need organic chemistry or you don't need organic compounds. So organic chemistry is actually the foundation of biochemistry, pharmacology, agriculture, and even cosmetics. Organic chemistry. So we have ladies that use cosmetics a lot. Makeups here, lipsticks here and there. All of those things have elements of organic compounds in them. So as a lady, you should love organic chemistry. Yes, you should love organic chemistry. Good. So we have it. The basis of biochemistry, pharmacology, agriculture, and cosmetics. So what are some sources of organic compounds? Yeah, sources of organic compounds. Subscribe to Learners Aid. Subscribe to the channel. Just hit that subscribe button. Hit the subscribe button. Good. Source of organic compounds. What are some sources of organic compounds? The first source we have here is natural sources, meaning they are born this way. These are organic compounds that are born the way they are. They are the natural sources born to be organic compounds. Yes. Then we, for example, the carbohydrates. These are basically obtained from nature. For example, from plants like sugar, oils, alkaloids like caffeine and vitamins. All of these are natural sources of what? Organic compounds. Then we have animals like proteins, fat, hormones, enzymes. All of these are also sources of organic compounds, but they are natural sources of organic compounds. They have microorganisms like penicillin, alcohol, and the drinks, the cheers, alcoholic beverages, antibiotics. All of these contain organic compounds. So the point is clear. We need organic chemistry so much. We rely on it. So it's no wonder that organic chemistry has gotten a unique and entire field for itself. Yes. Then it doesn't end there. Fuels, crude oil, natural gases, coal, all of these contain organic compounds. Is that all? No. So we've gotten natural sources of organic compounds. We also have synthetic sources of organic compounds. Synthetic sources of organic compound. So if you look at natural sources of organic compound, what are some synthetic sources? The opposite of natural is synthetic. Yeah, so subscribe to the channel. Let's push this channel so that we should get to more students that will benefit from lessons like this. So what are some synthetic sources of organic compound? When we say organic compounds are synthetic, it basically means they are made in the lab. So these are the compounds that are made in the lab. For example, aspirin, paracetamol, anti-malaria drugs. All of these contain organic compounds, but they are made directly in the lab. They have plastics like polythene, polyvinyl chloride, that is PVC. We have polystyrene. And even the bucket that you use at home, all of these stuffs are made up of what? Synthetic organic compounds. They are made directly from the lab. They have fabrics, nylon, polyester. So basically the shirt that you are wearing is organic chemistry. Yes, the shirt that you are wearing is chemistry. Basically, so the shirt that you are wearing is chemistry. So can you imagine? Can you just imagine that the shirt you are wearing is chemistry? So the idea that organic chemistry rules the world is really, really true. So dyes and paints. We paint our rooms with beautiful colors that we love. Yes, all of these colors, these dyes, these paints are synthetic sources of organic compounds. So you see? So I've given you so many reasons why you should learn, understand organic chemistry and really appreciate its position or its contribution to life in general. We have cosmetics. So there is no lady who can say with confidence or can justify his reason for not liking organic chemistry. Every lady should love organic chemistry because they love cosmetics. Yes, and it makes them look beautiful anyway. So cosmetics like lipsticks, lotions, shampoos, all of these are chemistry. All of these are chemistry. They have organic sources. So closing thoughts on this first section of our lesson on organic chemistry. What is closing? That carbon may be tiny. Carbon is atomic number 6 on the periodic table. Yes, may be tiny, but in the world of chemistry, it is actually the main character. It is the main character. It is the drama queen. So carbon is the main character out there. Yes, it is also the drama queen out there. And it doesn't end there. It is also the hero. Yes, the hero of the show. So chemistry has all of this in it. So the next time that you eat cookies, the next time you take your time to eat that your beautiful, delicious cookies, or you wear a shirt, or you take a pill, or even breathe in, the next time you do all of these things, thank organic chemistry. Say a big thank you to organic chemistry, because organic chemistry tends to be the foundation of all of this. So this brings us to the end of the fundamentals and introduction to organic chemistry. What will we be considering next or discussing next? So in the next few minutes that we have ahead of us, we'll be looking at classification of organic compounds. Classification of organic compounds, where we'll discuss hydrocarbons and hydrocarbon derivatives, aliphatic and aromatic compounds, saturated and unsaturated, open chains, and cyclic compounds. So now we are going to step up the gear. Yes, we are going to step up the gear so much, and you are going to learn a lot. Yes, we are going to make it so interesting. You will learn so much. So the first one was just history and telling you the reason why it's important. But now we are going to the parts that you are going to meet in your exams. Yes. So if you like what you've seen so far, subscribe to the channel. Yes, subscribe to the channel. Yeah, so let's move on. The next lesson. Good. So we've ended the first part. Let's look at classification of organic compounds. So this is a really fast-paced lesson. Classification of organic compounds. Yeah, are you ready? Hopefully you are. Are you ready? So let's see. Classification of organic compounds. So let's get started. So welcome to the Great Organic Family Reunion. Yes, that's how I started the note. Welcome to the Great Organic Family Reunion. Why do I say welcome to the Great Organic Family Reunion? Because if you pick organic compounds, some of them are straight chains, yes, and some of them are rings, and some of them are branches, and some are aromatic, while others are not very, very aromatic. So meaning if you pick the family of organic compounds, their properties and behaviors and attitudes and moods are different. They are not the same. They have different characteristics. Yes, they are different, although they belong to the same family. Some are straight chains. They are made up of links of chains. So we have carbon, linked in chains. Some form rings. They are the same organic compound too. Some form rings. Some form branches. So we have 1, 2, 3, 4. Then there's an extension from it forming a branch. So you see, they are all organic compounds, but their behaviors and properties are different. Some are aromatic compounds. They exhibit some aromaticity. Yes. So all of these are all organic compounds, but they have different properties and reactions. So scientists have to think really fast. They need to classify this organic compound, and it was really necessary for them to classify it. But let's revisit our historical background of organic chemistry a little. So back in the days, when chemists finally figured out how to tame carbon, that's story time. story time. So back in the days, compounds like, let's say, organic compounds or carbon is like a lion. Then chemists are these trying to tame the lion. It's not easy, but they were able to do that. They were able to tame organic compound by overturning the vital force theory. And who did that? Friedrich Wöhler. We already discussed that at length. So Friedrich Wöhler was able to turn down the vital force theory. Then they realized something very amazing. Not all organic compounds are made equal. They were all organic compounds, but they were not made equal. Some were chill and simple, others were intense and reactive, while a few, well, they have rings and smell nice. Yes. So imagine you have a lot of organic compounds to deal with. Then you realize that some of them are cool. Yeah, they are chill and simple. They don't have issues with people. They love to have it low and interesting. Others, well, they are very intense and reactive. And some form rings, some do not form rings, some have nice smell, others do not. So, well, scientists realize that, well, yeah, we need to do something about all of these. So chemists need to organize these organic compounds into WhatsApp groups. Yeah, not literal WhatsApp groups, yes. Not actual WhatsApp groups, yeah. You need to organize these organic compounds into groups. So all of you that are chill, go here. All that are reactive, move here. All that are, how do I put it? All that are having nice smell, move here. So they have to classify them. So that's what scientists have to do, like creating a WhatsApp group for all of them. And for them to put you in a particular group, you must exhibit some particular set of properties. That's interesting. So look at this. They classify them into hydrocarbons, hydrocarbon derivatives, aliphatic carbons, aromatic, saturated, unsaturated, open chain, cyclic. Yeah, just name it. So now let's look at them one after the other. Let's look at this organic compounds one, these classifications one after the other. So let's see. Let's look at the first group, hydrocarbons versus hydrocarbon derivatives. Hydrocarbon versus hydrocarbon derivative. So let's look at that really quick. Hydrocarbons versus hydrocarbon derivative. Good. So at the very top of the family tree, we have the hydrocarbons and the hydrocarbon derivatives. So let's pick the very first one, hydrocarbons. What are they? So these are the purest organic compounds. So hydrocarbons are the what? They are the purest organic compound. They contain only two things. And what are those things? Carbon and hydrogen. That is why they are called hydrocarbons. So hydrocarbons are basically organic compounds that contain carbon and hydrogen atoms only. That is why they are called hydrocarbons. So let's look at some examples of hydrocarbons. Some interesting examples of hydrocarbons. We have ethane, ethane, ethine. Good. Yes, maybe you don't even know how we came up with the name, but when we get to naming of organic compounds, you get to understand why they are the way they are. So let's look at the first one, ethane. Look at the elements that are found here. Ethane has carbon and hydrogen atoms present. Only carbon and hydrogen atoms. No other atom present. Ethane, carbon and hydrogen atoms only. Ethine, carbon and hydrogen atoms only. So if you meet an organic compound and that compound contains only carbon and hydrogen, then it is a hydrocarbon. It is what? Hydrocarbon. But let's look at this, hydrocarbon derivatives. We can compare hydrocarbon derivatives as the fashionistas of the organic world. We already discussed hydrocarbons as organic compounds containing carbon and hydrogen atoms only. So carbon and hydrogen atoms only. But hydrocarbon derivatives are organic compounds that are derived from hydrocarbons. I think you got that. Hydrocarbon derivatives are organic compounds derived from hydrocarbon, let's put it that way. So you can see that these are the fashionistas of the organic world. They started off as what? Hydrocarbons. They started off as hydrocarbons, but replaced one or more hydrogens with other elements. So let's look at an example. So we have ethane here. This is ethane, right? So this is ethane, 2 carbons with 4 hydrogens. So suppose one of these hydrogens, like this, the extreme end one, is removed and replaced with OH, then it's no more ethane, it has become an alcohol, specifically ethanol. So ethanol is an example of hydrocarbon derivative. So you have ethane, ethanol. Ethanol is hydrocarbon derivative. Why? It is derived from a hydrocarbon. So hydrocarbon derivatives are obtained from what? Hydrocarbons. So if you have not subscribed to the channel yet, quickly do your best to subscribe to the channel to support us. Yeah. So hydrocarbon derivatives are obtained from hydrocarbons. Another example is this. You can see that it starts off as a hydrocarbon, and this hydrogen here has been replaced with Br, a bromine. So this has become bromoethane. Bromoethane. It is a hydrocarbon derivative derived from hydrocarbon. Then we have amines. Amines. The hydrogen replaced with an amine to become ethylamine. So it's no more ethane, it's now ethylamine. So note, hydrocarbon derivatives are derived from hydrocarbons. They are derived from hydrocarbons. They are gotten from hydrocarbons. So basically, that's the idea about hydrocarbon derivatives. Hope you got that. So the next thing we'll be considering is aliphatic and aromatic compounds. Aliphatic and aromatic compounds. Aliphatic and aromatic compounds. So we've looked at the classification based on what? Hydrocarbons and hydrocarbon derivatives. That's the bigger style of classifying hydrocarbons and hydrocarbon derivatives. That classification is based on the element that is present. If it is carbon and hydrogen only, that falls under hydrocarbon. But if it is a hydrocarbon that has one of its hydrogens replaced with another element, they have hydrocarbon derivative. Now we have aliphatic and aromatic compounds. This classification is based on the structure and aroma of the elements or the organic compound. It's based on the structure and the aroma. So for aliphatic compounds, these are open chain non-aromatic rings. These are open chain or non-aromatic ring compounds. They can be straight chains, branch, or even cyclic, as long as there are no aromatic rings. When we talk about aromatic rings, this is something we'll be discussing in future lessons. So kindly subscribe to the channel. Kindly subscribe to the channel. We'll be looking at this extensively, aromaticity, the Haeckel structure. All of these things are stuff to be considered extensively in future lessons. But this is just the introduction to organic chemistry, so we will not be going too deep into stuff, but we'll be just doing the surface. You get the surface understanding very well. Then when we dive deeper, yes, when we are taking you deeper, you know where you understand what to do. Good. So for aliphatic and aromatic compounds, the aliphatic ones are the ones that are open chain. They are non-aromatic. rings, and they can be straight chains. They can be straight chains. They can be branch chains. So you can see that this is branch. We have 4 carbons, 1, 2, 3, 4, and there's an extension from these 4. This extension makes it a branch aliphatic. They have cyclic non-aromatic ring. So we can have an aliphatic compound that is cyclic but not aromatic. Yes, it might sound quite confusing, but when we start looking at what makes an organic compound aromatic, when we start studying aromaticity, it will make more sense to you. So this is an aliphatic compound because this ring is not aliphatic, it's not aromatic. So keep that in mind. It's not aromatic. So basically that is what, these are some examples of aliphatic compound. We have butane. The first one is butane. 1, 2, 3, 4. It has 4 carbons, only single bonded carbons. So it's a butane. This is 2-methyl butane. Why? Because you have 1, 2, 3, 4 carbons, and there's an alkyl group. Yes, alkyl group. We'll be discussing that one too extensively, so don't worry too much. You get to understand it at the right time. Just subscribe to the channel. So we have methyl group with an alkyl group attached to the butane, and it's one on carbon number 2. So you have 2-methyl butane. Then we have cyclobutane. This one is cyclobutane. So take note of this. This is very, very important. These examples that we've discussed, butane, 2-methyl butane, cyclobutane, they are hydrocarbons, at the same time aliphatic compounds. What that basically means is that when it comes to classification of organic compound, there is a high probability that some of these compounds can belong to multiple groups. So the classification doesn't mean if you are an aliphatic compound, there is no way you cannot be a hydrocarbon. No. Hydrocarbon only classify based on whether the organic compound has only carbon and hydrogen or not. Yes, so if it contains carbon and hydrogen atoms only, then it is a hydrocarbon. And then, if it is hydrocarbon, you ask yourself, is it open chain or is it straight branch cyclic, which is non-aromatic? Then it falls under aliphatic compound. So this is a straight chain aliphatic hydrocarbon. You get the point? So butane is a straight chain aliphatic hydrocarbon. It's straight chain because it is straight. Aliphatic because it's an open chain. And it's a hydrocarbon because it contains carbon and hydrogen atoms only. Hopefully that makes sense. Yes, hopefully that makes sense. Then, so this is aliphatic hydrocarbons. Yes, so these are examples of aliphatic hydrocarbon. Meanwhile, this is a branch chain aliphatic hydrocarbon. This is a cyclic aliphatic hydrocarbon. Now we've discussed aliphatic compounds. Let's look at aromatic compounds. Aromatic, aroma. So when you hear aromatic compounds, think of aroma. So aromatic compounds, these compounds contain at least one aromatic or benzene ring. Do not stress yourself. We'll look at what aromatic rings or compounds are and how to identify them. But you should just keep this in mind so that when it comes to detecting aromaticity to make sense to you. So benzene ring. Benzene is basically, let's see if I can get the structure for you. Yeah, this is a benzene ring. Hopefully it appears for you to see. So you have benzene ring here. Benzene is a hexagonal ring with alternating double and single bonds. A hexagonal ring with what? Alternating what? Single and double bond. So we have carbon, 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 carbon. So we have double, single, double, single, double, single in that way. So the bonds alternate. Double appears, they have single, double, single, double, single. So it has alternating double and single bond. So this is an aromatic compound. Funny enough, there was a reason why scientists named this an aromatic compound. They called it aromatic, not because they all smell good. Not because all of these compounds smell good, no, that's not the reason, but because early scientists noticed their nice smell. So early scientists of the time, they realized that all the compounds that they put under the aromatic umbrella, they had this nice smell. The smell were nice. So they named all compounds that belong to that group as well, aromatic compound. It was later on that they realized that some of the compounds qualified to be aromatic compounds but do not have nice smell. So the criteria for putting into aromatic compound now based on what? Electron delocalization. Something we'll be considering later on. So now it was based more on electron what? Delocalization. So we have an example here, benzene ring. Let's see if we can get other examples here. We have benzene, we have furan. Furan, then we have toluene. So you can see toluene, the only difference between toluene and benzene is the fact that the hydrogen here has been replaced with a methyl group. That's basically the difference between this benzene and toluene. Interesting. Good. Is that all? So benzene and toluene are aromatic hydrocarbons. Yes, benzene, can see that it contains only carbon and hydrogen atoms, so it's a hydrocarbon. And toluene also is a hydrocarbon, so it is an aromatic hydrocarbon. So the bottom line is you can have compounds belonging to multiple groups. Now let's look at saturated and non-saturated compounds, saturated and non-saturated. So this classification is based on how many hydrogen atoms the carbon is bonded to. It's based on that we have the saturations. So this is all about how many hydrogen atoms a compound can hold. So we'll be looking at that really quick. So what are saturated organic compounds? Saturated is just a fancy English word, meaning when we say something is saturated, we can think of it as having the maximum intake. Yeah, so there are more. So if you say a carbon atom is saturated with hydrogen, meaning it has the maximum number of hydrogen atoms it can bond with. And most of this time, the saturated organic compounds have single bonded carbon-carbon atoms. So saturated compounds have carbon atoms that are what? Single bonded. These are what? Saturated. Meaning they are saturated with what? Hydrogen. Let's look at some examples. Butane. Look at this carbon. All the carbons have hydrogens all around. There is no space. There is no space for more hydrogens to be added. So for an organic compound or a hydrocarbon, if the carbon-carbon atoms are only single bonds, they know they have a saturated compound. If they are only single bond. If you look at this also, 2-methylbutane, it is hot, saturated with hydrogen. Why? Because all the carbon atoms are having single bond. So saturated compounds, in saturated compounds, all carbon-carbon atoms or all carbon-carbon bonds are single bonds. That is the way to identify saturated compound from non-saturated, from unsaturated. So for saturated, look at the carbon-carbon atoms. Are they all single bonded? So single bonded. 1, 2, 3, 4. Single bond 1, 2, 3, 4. Single bond 1, 2, 3. All around the carbon atoms are single bonded. That makes it saturated, as simple as that. And the opposite is true. So if you look at this carbon, single bonded, single bonded, single bonded, as we've circled it like that. Good. So you can see that this compound is butane. It is saturated. At the same time, it is aliphatic, and at the same time, it is a hydrocarbon. So this alone belongs to all these three groups. So this is a saturated aliphatic hydrocarbon. This is a saturated aliphatic hydrocarbon as well. So basically, that is saturated for you. Now let's look at unsaturated. So for unsaturated, this contains at least one double or triple bond. So let's look at examples to that we could use to do the explanation. This is an ethene and this is an ethine. Zoom in and look at this. We have carbon-carbon, and in between the carbon, we have a double bond. So because of this double bond, this organic compound is an unsaturated compound, as simple as that. So for saturated, the carbon-carbon atoms have only single bonds throughout. Yes, there are only single bonds, but for unsaturated, it means there is at least one. So you can have carbon bonded, but if you find one double bond or one triple bond somewhere between the carbon atoms, then you are looking at unsaturated compound. So look at this. Double, this is triple. As simple as that. That's one basic difference between saturated and unsaturated. So these are also aliphatic, but they are unsaturated. So aliphatic, unsaturated hydrocarbons. So let's now complete with the shape of the molecule. That will be the last classification criteria that we'll be considering. We have open chains and open chain compounds and rings. This we'll just go through really quick. So these are like the spaghetti noodles, long, straight, and branching. So these are all straight chain or open chains. Yes, they are opened up. Look at this. They are opened up. But compare, look at this also, they are opened up. Just look at the diagram very well. Straight chain here, branch chains here, straight chain, branch chains here. Now compare that to the cyclic ones. Look at this. So this form rings, cyclic. So for the open chains, there are no rings in them. But for the cyclic, we have rings in there like cyclopentane. Good. And what? Benzene. So that's basically one interesting difference between the open chains and cyclic. For the cyclic, the carbon atoms loop back on themselves. So they form what? A loop, a linked loop. So that is an interesting difference. So this is a visual map to summarize everything we've discussed so far. Organic compounds can be classified into two. They can be classified into, let's get it, showing, into hydrocarbons and hydrocarbon derivatives. So all organic compounds can either be what? Hydrocarbons or what? Hydrocarbon derivatives. And when we consider the hydrocarbons, they can be aliphatic or what? Aromatic. And if you look at the aliphatic, they can be open chain or cyclic. And then if you look at the open chain, it can be saturated or unsaturated. And then if you look at the cyclic as well, it can be what? Saturated and unsaturated. So these are examples: alkanes, alkenes, alkynes, cycloalkanes, cycloalkenes, cycloalkynes, benzene, and alcohols. So this is a rapid-fired visual representation, really quick. Yeah, so this is a visual concept map of how organic compounds are classified. I think this brings us to the end of the intro and classification. So we'll end here for now, and the next 1 hour we'll resume the stream again and we'll continue with types of bonds in organic compound. Types of bonds in organic compound. For that, we'll be looking at the bonds that hold these organic compounds together. We'll be considering intramolecular and intermolecular forces that exist between these organic compounds. So thank you so much for joining. In our next lesson, we'll consider this bonding in organic compounds. See you in our next lesson. But before you go, subscribe to the channel, put us on post notification, and share the link with other students that you know will benefit from lessons like this. See you in our next lesson.